Great, thanks for the invite. It's great to be here with y'all and to talk about MOSAiC. So hopefully most of you know what that means, but if not, it's the Multidisciplinary Drifting Observatory for the Study of Arctic Climate. We'll get into what that means going forward in the next few slides. And the overall presentation here is I'll give a little background on MOSAiC. But I really want to focus on the links between MOSAiC and YOP. That's really the important focus here. So I'll start a little bit with kind of my traditional spiel for MOSAiC, but then we'll transition partway through. And I typically start with a couple motivational slides, and it really strikes me that this is really lost on this crowd. Talk about, of course, rapid sea ice decline and Arctic amplification, all the emerging operational needs we have in our model challenges, our limited observations, the linkages with the rest of the globe and Arctic change, all these kinds of things. And of course, it's all motivated by improving our models, our forecasts of weather and sea ice, our predictions of climate. We have to have all this physical understanding, and here's a list of processes. And to me, I get to this point and I'm just like, well, am I talking about YOP or am I talking about MOSAiC, right? It's really the same thing. We're all motivated by the same things. And this was the foundation upon which we really crafted programs like PPP and YOP as well as MOSAiC. And so we all know the background, right? And it's a shared background between this community and MOSAiC. But it was based on that background that we started to develop the concepts for an expedition into the Arctic. And that expedition we knew from the start had to be very international in its nature. So it was organized through committees like YOP here, or like the International Arctic Science Committee, and it took many years to develop. So a similar kind of lifeline and timescale as the PPP process as well. We knew that the whole program, the expedition, had to be interdisciplinary. This is really important. The atmosphere, the sea ice, the ocean, interacting through physics, through chemistry, through biology, and all these many different processes. The program had to be multi-scale in nature, looking at small scales, fine details, at model grid box scales, at pan-Arctic scales, to really understand the kind of multi-scale linkages across the system and how do we scale our understanding of those. It really had to integrate observations and models from the start and throughout. That's really important as we think about observational activities, to really base them on our model needs and our model objectives going forward. And lastly, we really wanted to look at the full annual cycle. The Arctic is an interesting place to go. It's very easy to go there in the summertime, and therefore we as a community have observed the summer very frequently. But to really understand the full annual cycle, these kind of interseasonal linkages, preconditioning of the sea ice, things like this are really important to go there and to understand how the seasons are interacting with each other. So these were some of the basic concepts for our expedition design. And importantly, of course, all of these bullets are influenced by YOP and the Polar Prediction Project. So as far as MOSAiC science, there's a little schematic here with lots of different processes shown, and we really tried to look at pretty much all the processes that were involved in the Central Arctic system, but all organized under one overarching question: what are the causes and consequences of an evolving and diminished Arctic sea ice cover? So sea ice is really the nexus here. It's the main focus, but we're looking at processes that are interacting with the sea ice, and then importantly, what happens to the rest of the system as that sea ice is declining, right? So it's kind of processes in and processes out. Okay, so what happened? Our year in the Arctic sea ice, this is our expedition into the Arctic, late 2019 until late 2020. So full year, we took the Polar Stern icebreaker, a really fantastic research icebreaker from the Alfred Wegener Institute in Germany. We took it out into the Arctic sea ice, drove into the ice, found a parking spot, turned off the engines, and passively drifted with the ice across the central Arctic on the transpolar drift over the course of a year. And you can see the trajectory here with some nice colors in the bold line there. That's the passive drift of the ship with the sea ice across the Arctic. And each of those colors is a different leg of the mission. We rotated people in between, bringing other vessels out there to bring fuel and supplies and food. And one thing that you'll see if you study the dates there is we actually made it across the Arctic much faster than planned. And that's in large part due to it was a very strong, positive Arctic oscillation year, for those of you that understand such things. Basically, the circulation pattern was set up in a way that the winds blew us across the Arctic faster than planned, much faster, for example, than Nansen took. He took 3 years to do this kind of a path, more than 100 years ago. So we got all the way across the Arctic into the Fram Strait by the end of July. And we didn't really want to go home, so we took the ship back up near the North Pole, and you can see the little purple squiggle there. That's to end out the year. We didn't want to leave the ice yet, so we took the ship back in to end out the year. So this is the context for MOSAiC, where the ship drifted. And I'm going to take you on a little bit of a journey. And this will be mostly pictorial here to start with. So we headed out into the Arctic sea ice. Fantastic view of the ship here. And we were in search of an ice flow. We tested out a number of them, but eventually found an ice flow that we felt would be suitable for a year drift project. This had to have special characteristics, of course, to last for a whole year. Once we found that, we started setting up all kinds of equipment out on the sea ice, buoy stations, looking at the ocean, at the ice, the atmosphere, all kinds of devices. You see the ship in the background. We set up a lot of cities out on the ice: Met City, Ocean City, Balloon Town, all these different areas of doing different types of research out on the ice. And then we started a very comprehensive physical measurement and sampling program. Lots of instruments on board the ship, collecting continuous observations, lots of people going out on the ice, collecting snow, collecting water, taking them back to a laboratory and analyzing them. We really tried to collect and sample everything we possibly could out there. Here's a great picture of some of those samples. This is, you can see a bunch of biological critters in these jars here, and this is sampled in the middle of winter, providing us this opportunity, for example, to understand what does happen to the biology in the middle of winter. Right? It's a really interesting question, and we have a great data set to look at questions like that. Here's another fantastic wintertime photo taken by Michael Gallagher, who's here in the room. Just thought it was a pretty photo. One of the key themes is ice dynamics, early and often. Right? You can see the ship here. You can see leads going right through the middle of our camp. And this kept happening over and over and over. And it was quite a challenge, as you can imagine, to keep your instrument out of the water and to keep it operational. So this really kept us on our toes. But on the other hand, this is the Arctic, right? It's right there, happening right underneath our feet. So it was really a tremendous opportunity to be out there embedded in this sea ice that's changing, that's becoming thinner, that's becoming very dynamic. Melt season, you can start to see the sun out more. A really fantastic time. You see the outlines of the MOSAiC flow here. It was about 1 kilometer across at this time of year, slowly being whittled away over the course of the year to this small size of 1 kilometer across now. Lots of really fantastic pictures here of some sampling, some ice coring going on, looking at biology and physical processes, people sampling and transects along the ice flow to look at ice thickness, snow depth, melt pond depth. Here's measuring surface albedo over a variety of different surfaces. In the foreground here, people sending devices down into the ocean to look at ocean structure, and in the background, those people are flying unmanned aircraft to sample the boundary layer. Here's a fantastic view down underneath the sea ice. In the summertime, there was this tremendous layering effect. Fresh water on top, salty water below, inhibiting the mixing of heat and of gases. Here's a picture of, we had a suite of devices that basically emulating satellite observations so that we could better understand what our satellites are telling us about the Arctic. So you've seen a sampling here of the different kinds of things we're doing out there. And I'll just give a little brief perspective here on some of the data over the course of the year. This is the annual cycle at MOSAiC. So you see here the full year, and basic meteorology, pressure, temperature, winds, shortwave radiation. In the gray is shading from the ERA 5 along the MOSAiC drift trajectory. So you can kind of see the climatological context over the last decades based on ERA 5. And the red line is this kind of smooth data from MOSAiC about where we fit into the context. And In the pressure field in the top panel, you see there were all these little black squares. These are kind of pressure centers, cyclones that affected us in some way. You can see a number of times when the pressure got much lower than we would typically expect from Era 5. So it was kind of a stormy time for us out there, especially in the wintertime. From a temperature standpoint, the second panel there, you can see kind of a traditional, typical kind of variability, some extremely warm events, some extremely cold events. So it was definitely a unique year out there when viewed from the meteorological perspective. Just summarizing a little bit by the numbers, MOSAiC had 20 nations involved in the funding aspect and 37 nations involved in terms of the people that were out there. We had 7 icebreakers and ships involved, more than 80 institutions involved, more than 400 people made it out to this ship as it was out into the ice. And the budgets are hard to quantify. Big numbers, and they're growing as we continue to invest in the science. So it's a pretty big program, pretty significant international investment. And so this is kind of a summary slide that I often give for MOSAiC, typically after a much longer presentation, but I wanted to kind of touch on that here in the middle of my presentation before pivoting a bit. So the MOSAiC year was one with many challenges, COVID notwithstanding, right? But also some very distinct successes. And we were out there in this thin, dynamic sea ice, and this really gave us this opportunity to be in the middle of the Arctic and its change. We did tons of science. We really packed in as much as possible, and in many ways, we're probably too ambitious in our design, but we really came through with a lot of hard work. We had broad participation from the international community, from many different agencies, interdisciplinary science. We had lots of communication and media and education involved. We built a ton of capacity, a whole new generation of scientists that know how to do field research out in a very, very dynamic Arctic. And we built some new concepts for how do you actually study a thinning sea ice pack. And most importantly, we brought home a legacy of data. Right? This is a fantastic data set. A lot of that's available now publicly, and importantly to you all the data must be made available by January of this coming year. Right? So it's out there for everybody to use, and please do use it. Right? The whole reason we did it is for you to use this data. So please go find the data and please use it, and ask questions. There's a lot of people within the MOSAiC community already that understand that data and that can help you to better use it in your activities. So I want to pivot now and focus a little more on this relationship between MOSAiC and YOP, and what I'll characterize as a very successful collaboration. And I'll touch on a few different kind of elements here of this collaboration. We'll start with the design. How does one design an expedition like this? Well, the design was multi-scale in nature. All right, so we have our central observatory. This is a ship. This is very detailed observations at one discrete location, looking at the full column extending from the atmosphere, ice, ocean, and all the pieces in between. And that very much maps onto some of the high-resolution types of models, large eddy simulation models, single column models, et cetera. Our design also had this distributed network. I'll talk a little more about that in a minute, but it's distributed observations over, say, a model grid box scale, so we can understand heterogeneity in the system, and that maps onto perhaps regional models. And then we had this concept of linking our observations with the network of observatories around the Arctic, with other ships, with aircraft, with satellites, to really get this pan-Arctic perspective that helps us to scale up to the very large-scale Earth system models. Right? So multi-scale model design, multi-scale observational design, very much influenced by discussions we had here in this community and in other modeling communities. So this coordination of modeling and observing priorities right from the start, that was really important, and a strong link between MOSAiC and YOP. So our distributed network. Here's a schematic of our distributed network as we started out the expedition. The ship, the polar stern, is where the red star is in the middle, and all these other little symbols are buoys or other kind of multi-sensor, multi-installation stations. Out on the sea ice, you see the range rings there. The outer ring is 40 kilometers, so we had tons of equipment out there on the ice. This has never really been done in this kind of a this kind of detail. And so this allowed us, you can imagine this is a model grid cell or 2 or 3, depending on which model you have and what your resolution is. But you can imagine this density of points across that array provides the kind of information that we just haven't had before. So often we go out there with one observing station and we try to evaluate a model with that. And a lot of people, especially from the modeling community, kind of laugh at it, and rightfully so. But at least here we're making an attempt to find multiple perspectives across the same kind of scale so that we can better inform that variability. And so this was really successful, especially in wintertime. As the year evolved, dynamics took out a number of these nodes over time, but that's just kind of the inevitable part of being in the Arctic, I guess. Another concept in the design that's really important is this scaling concept. And so here's just an example, right? So I myself do a lot of radiation measurements. We'll go out there, we'll put a radiometer at 2 meters, and we'll look at the reflected sunlight from the surface, and we'll get an albedo out of that. And what does that mean, right? It's a 2 meters little circle on the ground, and how useful is that? Well, here's a great example of using drones then to start at a certain height over a certain surface. Maybe you're a melt pond, maybe you're over sea ice, and to go vertically higher and higher, which increases the view of the radiometers, the footprint of the radiometers, to look at the albedo in this case. And so what's plotted here is upwelling irradiance that's measured by the system, and the colors are color-coded by the albedo of the system. And what you see is this convergence at about, let's say 40 meters height, which is kind of a representative footprint below that. So we actually see that within an ice flow, you can start with lots of different types of albedos over the melt pond or over the sea ice. But at some point, at some scale, it starts to become representative of the ice flow. And then, of course, you can imagine the next scale up, right? You start combining multiple flows, and we're actually linking with the satellite community to take that next step as well. So we're trying to put together the pieces of a puzzle that's this kind of multi-scale approach. So we understand the observations, how they fit together, and how they scale up to something like a model grid cell scale. So that's a really important thing that's part of the design here as well. Another successful collaboration is in the implementation, actually out in the field. And the first one would be SIDFEX. And fortunately, we're going to hear all about that in the next presentation, so I'll let Helga take that one. But I just want to emphasize here that the SIDFEX was basically drift forecasting for the sea ice. And that was really important for us as we were in the field to understand where we might be going and how we could plan our efforts to basically accommodate that. And this was really important as we started to get near the ice edge, for example. So we'll hear about that in just a minute. Another important aspect of the implementation is what we've already heard about this week, the targeted observing period. And I really want to applaud PPP and YOP for the flexibility with this, right? Initially, there were the SOPs, and we had the whole mission here to go do these SOPs, and, check, we could just call it done. But it turns out that we actually wanted to go for a little bit more, and we did. And we put forward this notion of TOPs and got other, sounding stations involved, and this actually turned out beautifully. Nature really cooperated in this case and gave us this tremendous case. We saw from Gunilla yesterday about some of her studies with this case, and there are a lot of other people that are looking at this case, focused on this warm air intrusion in middle of April that really affected the MOSAiC site. It changed the circulation, brought a lot of warm air, it brought a lot of aerosols, it really affected the atmospheric chemistry. It started to push the system towards the melt onset, all these other features, right? So a fantastic kind of event that we really, I think, within the YOP community had the foresight to be ready for that. So it really turned out for us. More successful collaboration. And here I'll touch on some of the science. What kind of science are we doing out there, and what kind of priorities do we have? And so, we talk about priority processes. And again, I listed a bunch of them down below here. And, these priority processes are shared priorities that we all have. And importantly, MOSAiC has come home with this fantastic data set to really dive into those processes. And importantly, the wintertime part of that, right? Looking at these processes in winter and as they evolve over the rest of the season. So I'll talk about a few different types of kind of scientific focus areas here. Atmosphere ice dynamics. And in the following slides, I'll show some plots, some figures. I don't really expect you to digest those. I'm going to go through them pretty quickly. I'll tell you the main points, right? It's just to kind of to illustrate some of these. So atmosphere ice dynamics. We had some cyclones that affected us out there, some storms, right? I already told you we had quite a few over the course of the year. Here's some nice weather maps, satellite images of some cyclones there, and we measured profiles of winds. We measured momentum transfer at the surface across multiple nodes in arrays to really understand how those large-scale circulation and the winds are kind of translating themselves to the ice. And then we have our array of observations, our distributed network, with a number of different buoys in the array. And you can imagine making little polygons. And so you can see there are 3 polygons there connecting dots in the array. And you can imagine just tracking where those go over time as you get events that come through. And here are 3 different panels with 3 different size polygons in that array, looking at in colors the divergence, and in the black lines, the total area of those polygons in the array. And this is a long time, many-month time series here, but you see lots of events there. You see changes in the shape of those different polygons. And this is actually really important for us to understand at multiple scales how large-scale atmospheric features translate themselves into the movement and deformation of the ice field. Again, at different scales, right? This is exactly the kind of information we need to know to help improve our models and how they represent sea ice. So a huge opportunity here for the dynamic side of things. From the thermodynamics, let's look at that a little bit. And here's a case of about 25 days in the fall of 2019, where we look at, in the top couple panels here, over these 25 days, these are representing clouds. We had clouds there. Okay, these mixed phase clouds. The third panel shows that we had liquid water in those clouds. This is the super cool liquid water that is part of these mixed phase clouds that we very much struggle with our models to predict. But then in the bottom panel, I'm showing radiation, right? These clouds, this liquid water, is a big hammer on the system. It brings this big radiative effect. It blankets the surface. It warms the surface, right? These clouds warm the surface. So a big radiative effect from the clouds. And then we can trace that through the rest of the system. How does everything else respond? How does the surface turbulent heat flux respond to that radiative forcing from clouds? It turns out it's a really big response, and a big response in the conduction through the sea ice, for example. It affects the total energy budget of the ice. It affects the surface temperature. And in the bottom panel here, I'm showing temperature profiles through the ice itself. You see this kind of propagation of these thermal signatures through the sea ice that are related very much to atmospheric variability and clouds. And importantly, as you modulate the temperature structure of the ice, you're also modulating the ice growth process. So understanding this kind of coupled system, extending from large-scale circulation through clouds and radiation, energy budgets, sea ice thermodynamics, and sea ice growth. It's a really coupled process, but we have to understand it if we want to know what's happening to the sea ice. Snow and its distribution. Snow is a big topic as I think we're starting to appreciate more and more as a community, snow on sea ice. So we measured snowfall out there, and Barbara showed a nice presentation a couple days ago about the challenges in measuring snow, and indeed we had some big challenges as well. It's very windy out there, you can see in the last picture. But we're making, I think, important strides here to understand things and link this kind of snow as a moisture sink from the atmosphere, but a source for snow on the surface. How is that snow distributed spatially? It's deep over here, it's shallow over there. How does that affect the thermal conductive properties of the ice and snow? How does that affect the albedo evolution over the course of seasons? How much of that snow is lost into leads, for example? So again, a very kind of cross-cutting theme here that I think is important for us to understand our observations, but then capture this in our models. 2 minutes, all right. Did I get back my, oh boy. All right, melt season onset, I'll skip that one. So another successful area, model studies and assessment. This is an important area, of course, for these communities. Data assimilation, we heard some data denial experiment discussion in the last days. We haven't really done much of this yet with MOSAiC observations, but we have a ton of radio soundings 4 times a day in the Central Arctic to really dive into data denial experiments, data assimilation studies to understand the effect of other observations. Been doing some great back trajectory modeling to understand the source regions and processes along trajectories that lead to some of these important clouds. We've heard all week about MODFs, data files where we're packaging the data specifically for model evaluation, and I'll leave that one at that. We've heard about it a lot all week. And here's some work that Amy actually is doing, and we'll hear from Amy later today, I believe, to really look at, we're using some of these data in process relationship types of evaluations and assessments of models. And it's a really exciting story, and I really will encourage you to listen to Amy later today to see the details, the process details that we can pull out of the observations and then use that in a very sophisticated way to understand the details of how our models actually represent key processes in this coupled system. And there are so many other model studies going on, model-based research, large eddy simulations, we've got process models in action, we've got coupled single column models, regional model assessments, with many different thematic objectives, nudged global climate models, we heard from Felix a couple days ago here already, evaluating reanalyses, and so much more. And many of these are led by people in this community right here, using MOSAiC data, right? So a great partnership for model use and development. And so I just want to summarize by saying it's been a really tremendous and successful partnership between MOSAiC and YOP in all these ways that I list here, and I didn't even go into some of those. It's been, totally a success, and I really want to thank the PPP and YOP because this partnership was actually really important on the international stage, right? It took more than a decade to justify MOSAiC and to get it actually supported, and having a community like this that's a user community that says we actually need this data was very important in that process. And without that, I'm not saying it wouldn't have happened, but it might not have happened, right? It really did take a community like this to say, these are the data that we need, and we want to support this. And so that really got the ear of the funding managers and the key institutions. And so I want to thank you all for your role in making this all happen and invite you to continue to be part of the story. So with that, I'll say thank you and happily take questions.
Thanks for that, Matt. That was really super interesting. Do you have some questions on the floor? Again, just a quick reminder, please use the 2 microphones if you do have questions. People are thinking. There's no questions online yet either. But yeah, please, people online, feel free to ask questions too. Maybe I'll start things off a little bit, Matt. So I remember talking with you during the planning stage of this, and there's all these different ideas about the distributed network and thinking about what happened with Sheba and the new Arctic, the ice is thinner, how we can deal with it. And you show these pictures of the leads forming and the challenges. I was wondering, given all of that and all of the different, I guess it's so huge, it's hard to take it all in, all the different efforts in MOSAiC. But given all of that, if you went back and were to do it again, are there some key things that you'd do differently?
Yeah, and I think this is working now. Yeah, that's a great question, and indeed, yes, there are. I feel like over the course of a decade of planning, we were planning for that Arctic, and we got this Arctic, right? I've been in the sea ice quite a bit, and we all know the ice is getting thinner, it's getting dynamic, right? We knew that going into it, but yet it was more than we thought, right? So we were too heavy on the ice. We need to be lighter, we need to be more mobile, we need to be more autonomous. And these are just lessons that we need to learn as an observing community about how do you deal with the current ice pack. And these are things that we didn't quite get right, I thought. We could do better, I guess. And so we need to continue that. And that's one example.
All right. We got a question over here. Please come up and use the microphone.
I'm just wondering how good the links were between the MOSAiC program, the winter program, and CaliUp and CloudSat overpasses. Did you use that data and use it to better understand some of the things the large-scale things that you were seeing?
So, unfortunately, we were in the hole, right? So, those fantastic cloud sensing satellite observations go to 82 degrees north, and if you looked at our map, we were most of the time north of that. So that inhibits a little bit of comparison with those specific satellite platforms. But certainly we've used those for kind of the margins of the Arctic basin. So yeah, those have certainly informed a lot of studies and a lot of the instrumentation and the comparison with those instruments. So I think it does allow us to kind of upscale some of our perspective by bringing in those kinds of observations, yes.
Do we have another quick question on the floor? Oh, here we go. Please.
Thanks, Matt, for this nice talk, and I think it's already a success, MOSAiC. So I have a question. So when a MOSAiC in the southern hemisphere?
Sorry, what is?
A MOSAiC field campaign in the southern hemisphere, in the south.
In the south, yeah. You know,
So I think you are the good person to organize.
every time we come back from the field, everybody says, what's next, right? We keep saying that. And my answer to that is have fun. You know, somebody figure out what's next and you do it. But there has been actually discussion about that, right? So we had, you know, a MOSAiC meeting not too long ago, and of course the polar stern goes south a lot, and there's a new polar stern on the way and all these great things. And so, yeah, the gears are spinning to do something like that in the south. Again, I'll say to you all, you have fun with that. Sounds like a great experiment. I'll cheer it from the sidelines.
Okay, thanks. I think we're going to have to move on, but maybe another round of applause for Matt. That was very interesting.